Hey guys, it is Mr. Van Loo, and we're going to take a look at the topic 8.2 handout. Look at some answers. First thing you want to make a note of is we're going to be using Wiens Law fairly extensively, and that is given by this equation where peak wavelength times temperature is equal to a constant, 2.90 times 10 to the negative 3 meters Kelvin. This peak wavelength, you'll remember, is shown on a distribution of energy versus wavelength, and they usually look something like this. And the peak wavelength is just the maximum amount of energy, which would be like right around there. Okay, so that is what we're dealing with Wiens Law. Please refer to my previous lectures or the book if you need a little reminder. Okay, for 8.7, we are asked to find the peak wavelength of the emitted radiation of 3 bodies. The first body is a human body, the second is the Earth, and the third is the sun. Okay, so first we are looking at a human body, and since it is not a corpse, it will be at about 37 degrees Celsius. Always, always, always use Kelvin for Wiens Law. Always. Okay, once we know our temperature in Kelvin, it's a very simple matter to rearrange the Wiens Law equation into this form, and there's our answer, 9.4 times 10 to the negative 6 meters. Okay, the Earth has a maximum wavelength given by its temperature of 288 Kelvin, its surface temperature, and the math there will give about 1 times 10 to the negative 5 meters. Finally, we have the sun, and its temperature, it's quite large temperature of 5,800 Kelvin, will give 5.0 times 10 to the negative 7 meters. Note that the ranges of temperatures here are not all that different. So if you get an answer that is way outside of this kind of narrow range of wavelengths, sorry, not temperatures, then that would indicate that maybe you've made a mistake and you want to double check your math. Another important note here is that your storage function in your calculator is very, very useful, and you should take advantage of it wherever you can. So 8.8, by what factor does the power emitted by a body increase when the temperatures increase from 100 degrees Celsius to 200 degrees Celsius? Well, here it would probably be useful to exploit a proportionality. So I've written the equation for power here. This is given in your data booklet. Note that I've also converted both temperatures to Kelvin. Do not forget to do that, because paper 1 questions in particular will predict that you are going to not convert to Kelvin, and they will give you the incorrect answer, okay? Because they know that students are going to forget to do that, and they want to catch those students out. Right, well, if this first equation is true, then this proportionality must also be true. And that is the proportionality that we're going to exploit to find our factor. Okay, so initial power divided by final power will be equal to initial temperature to the 4th power divided by final temperature to the 4th power after some very simple algebraic manipulation. From this point then, we just plug in our values, and we will find that we have an increase in our factor, our increase in our power by a factor of 2.59. So it's just a ratio. All right, Taking a look at problem number 60, and this is from your hotter text, as you can see by the blue, slightly blurry text. Star has a radius of 8.3 times 10 to the 7 meters and a surface temperature of 7,500 degrees Celsius. So first, calculate the power that it emits. So in order to do that, we have to find its surface area, which I've shown with this first calculation here. So this is the kind of thing that examiners are looking for when they give you marks, these kind of intermediate calculations. I could just plug this directly into the equation below, and that would be fine. It would give me the correct answer. Okay, I then also want to convert temperature to Kelvin. Again, super important. Do not forget to do this. Super, super, super important. Okay, for A, this is the equation. Again, this is in your textbook. It's the Boltzmann power equation. So power is equal to emissivity times the Stefan-Boltzmann constant times surface area times temperature to the fourth power. So here we have to make an assumption, and this also answers part B. We are assuming that the emissivity of our star is 1. And that indicates that it is a perfect black body. And that is a reasonable assumption for a lot of these problems. If emissivity is not given, just go ahead and throw 1 in and see what happens. You'll usually end up with the right answer. Okay, next we need the Stefan-Boltzmann constant. That is in your textbook as well as in your data booklet. Okay, the area we've already calculated. The temperature we have converted to Kelvin. We will find that our star has 1.8 times 10 to the 25 watts. This is not super different from our own sun's power output, which you will recall is about 4 times 10 to the 26 watts. Okay, part B we've already discussed. C, what is the intensity at a distance of 2.4 times 10 to the 12 meters from the star? So here we just need to recognize that intensity is equal to power divided by area. And the area that we are interested in is the area of a sphere with a radius equal to our distance from the star. Okay, and that's going to give us our power at any distance from that star. Okay, so we've already seen this equation in my previous lecture, and here we're applying it. So once again, another variable that might be handy to store is the Stefan-Boltzmann constant, 5.67 times 10 to the negative 8. Right. Next page. If the temperature of an object increases from 285 Kelvin to 312 Kelvin, what is the percentage increase in its emitted radiation? Here we just use the same mathematics that we already used previously, and there's no sense in deriving it a second time. Okay, pretty straightforward. Second, B. An object is at 20 degrees Celsius. To what temperature would it have to be heated to double the power of the radiation emitted? Okay, so here, again, we're assuming that our body, so we're assuming that our body has an emissivity of 1. We're ignoring the area in this case, and the reason why we're ignoring the area is because this is just for any body. In fact, what we have here is kind of a proportionality, and maybe I should have set this up slightly differently. In any case, you'll see here that if we plug in our temperature, if we rearrange this equation down here at the bottom slightly, we will find that temperature is equal to the fourth root of 2 times our power divided by emissivity divided by Boltzmann's constant. Okay, and that will give us 348 Kelvin, which we then convert to 75 degrees Celsius. Another alternative is to use the mathematics shown here in B. It's a bit more elegant, but either one is going to work. So take a look at this, work it over. Let me know if you have any questions. Okay. When the current through an incandescent bulb is turned on, the temperature of the filament will rise until thermal energy is radiated away at a rate equal to the electrical power provided. So we can find the operating temperature of a 40-watt light bulb if the filament has a surface area of 1.2 times 10 to the negative 5 meters squared. This is an interesting problem because if we rearrange this slightly for temperature, what we're going to find is that your average light bulb has a tremendous temperature, and this is kind of shocking, 2,600 degrees Celsius for an incandescent bulb. That is not an LED bulb, and it is not a compact fluorescent bulb, but an incandescent bulb. They're not terribly energy efficient, and it's largely because they need to be very, very hot in order to get a temperature close to the visible wavelength of light. Note here that you may find that a fourth root is easier to enter as an exponent. I usually use exponents rather than square roots or third or fourth or fifth roots or whatever, just because it's easier, it's faster. But use your calculator as you like. Okay, 64. We're given a temperature and we're asked to find the wavelength of the emitted radiation. So this is very straightforward application of Wiens Law, not really much worth commenting on here. Part B, if you increase the temperature, or decrease, in this case, the temperature, here decreasing the temperature will be a kind of redder bulb, I guess you would call it. In this case, by increasing the temperature, it's more blue. Okay, that is it for this handout. Please let me know if you have any questions. You have already seen these answers, I believe. Okay, have a great day, guys.